Test, 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 test. Test, test, test. Okay, good. If you don't mind.
Okay. Something like that. It's okay, good.
That should be good. Yeah.
Okay.
Can you speak?
Раз, раз. Раз, два, три.
And this should, you can slide in your pocket or wherever's convenient.
Okay. Okay.
Okay, great. So we're very happy to have Sergey Kulagin with us, who's going to talk about the nuclear EMC effect. And so, yeah, please.
Thank you. Let me thank our organizers for inviting me for this meeting, a very lively meeting. In agenda, the title is somewhat cryptic, so the title of my talk called Kulagin Petty Model, but I don't know if it's known. But this is the subject I would like to talk about, and this is what model, what we try to do in a collaboration with Roberto Petty, the modeling of nuclear effects in electron and neutrino scattering. So let me. This is the plan of my talk. It's probably go beyond my capability to cover everything, but I'll try at least to cover the electron part of this. So I would like overview, just give a brief overview of data on nuclear effects in electron and muon scattering, and then proceed with discussion of the mechanisms, basic mechanisms, which are the background of these effects, and describe the model which we have for this, and then discuss the predictions and performance of that model for data. The model was developed on quite some time ago, but before the GLab data was released. So, but we did look at the GLab data. So this looks like a prediction of the model. So it's not a fit. So we have done some calculations for this, and I will discuss this. And also, I would like to, if I have time, so I would like to discuss predictions for Drell-Yan reactions and neutrino deep inelastic scattering. So this is what I know about data. So the data exist in the form of the ratios. Well, data of course exist in form of cross sections and structure functions, but the ratios is the tool which is usually used to measure nuclear effects. So as far as the targets, there is quite a spectrum of targets, from hydrogen, from deuterium to lead. There is data from fixed target experiments of different energy performed at CERN, Fermilab, at SLAC, and at DESY, and recently at GLab. So the kinematics is quite wide, so that it covers the region of starting from quite low x, from 10 to -4, but this low x is for fixed target experiment is usually correlated with low q square. And coming to the region with which is kinematically forbidden for free nucleon. So there is about 800 data points which can be analyzed if we apply a cut of q square above 1. The neutrino, there is a nice piece of data coming from Drell-Yan experiment, which probes directly the anti-quark distributions. which is not accessible in electron and muon scattering. And there is some data coming from neutrino experiments. If I have time, I will discuss this. So this data on cross sections from CERN experiments and I mean Chorus and NAMAT and Fermilab experiments, CCFR and NUTEV. And actually, the old bubble chamber experiment is also useful. So, and this is so far the only experiment which gives us the direct measurement of nuclear effects. So they actually measured the ratio of neon and deuterium targets. And I should also mention that there is strong effort to measure the ratios, the nuclear effects in the Minerva experiment, and I think it will be released soon. So this is how the data looks like. So it looks like the shape is it has if you look at the data as a function of Bjork and X, so it has kind of oscillatory behavior. So the cross sections gets positive and negative corrections depending on the kinematical region. There is some kind of standard classification of these effects, which is written here. So that the small effect is usually called shadowing effect. The large X region is associated with the MC experiment, and the larger X is usually attributed to Fermi motion correction. I will try to argue that indeed, so these different kinematical regimes are associated with different background mechanisms. So the nuclear physics of these corrections is different. So I should also mention that recently there is data coming from GLAB. So far, only the data on light nuclei published in the form of the ratios. So it covers the region of large X and has good statistics. So this is barely deep inelastic region. So it's almost on the border between the deep inelastic and transition and resonance region. So speaking about this new data, so this is how it looks like. So here I plotted the results of the older measurement at SLAC, which is in black, and newer measurement in red. So the slopes are consistent, but you can see by eye that the normalization is somewhat different. So actually, if we had a look at this issue, that trying to figure out how the different the normalization of those two data sets. Well, actually, 3 data sets. So if you talk about the large X region, then useful data sets are those coming from E139 experiment, from old data and from NMC, and also JLab. So what one can conclude by looking at the data, that there is some small, about 2%, and this is you see statistically looking at the data by rebinning the data to larger bins, and that the normalization is somewhat different. but the normalization error is not shown here. So I'm not saying this is a problem of the data. So this is just that what is published. The central point is not fully consistent with slack data, but the slopes are consistent. So if you talk about possible mechanisms for nuclear deep inelastic scattering, then it's useful to look at characteristic times and longitudinal distances involved in this process. And it's a simple exercise, actually. So we just look at the correlator of the current and study the exponent which is there. And then for this particular kinematics, if we see it in the laboratory, in the target rest frame, then we see that this process has the small transverse size of if q squared is large, and so it proceeds close to the light cone, but actually the longitudinal distances and the times, characteristic time which is involved in the process. So the characteristic time is just the average, in some sense, average time between absorption and emission of the photon in the Compton amplitude. And longitudinal distance has the same meaning. So they are not suppressed by large momentum transfer in the lab frame, but actually are given by so they are of the order of hadronic scale. And are given not by the momentum transfer, but by the Bjorken X. So by looking at this, so this is just a simple exercise. So if we have X large enough, then for large X, so time is sufficiently large on the nuclear scale, and then we can try to apply the incoherent approximation, impulse approximation to calculate the cross sections. But if X is small, so the characteristic time is large, so the process is extended in time, so the intermediate states have enough time to live in the lab frame and develop a coherent multiple scattering processes. So here we have to do with coherent effects and calculate them somehow.
M in that case is nucleon mass?
Yeah, thank you for a comment. M is a nucleon mass, not nucleon. So M is a nucleon mass, thank you. So here is the sketch how we, so let's look at the large X region. So here is the sketch how we could possibly proceed. So sorry to bother you with these details. So I just would like to comment about a couple of things here. So we have a few problems to face when we try to calculate the Compton amplitude. So this is a typical expression for impulse approximation. So we have, in order to calculate the nuclear hadronic tensor, so we have to know the nucleon Compton amplitude, or its imaginary part, and also the correlator, nucleon correlatory in the ground state. So the equation looks like that.
Sergey, I believe there's a laser pointer there on the table.
Here? Oh, thank you. Well, actually, I had a problem with this pointer, so it's too bright, but now it doesn't work. Oh, I'm sorry. Okay.
I think there was another one that came in.
Oh, I have a pointer, so thank you.
Okay, you've got the.
Yeah. Okay, so that's so what about this amplitude? So this, we actually know this Compton amplitude on the mass shell, on the nuclear mass shell. So when we take the matrix element of this amplitude with the Dirac spinors, which correspond to the physical states of the nucleon, and average over the polarizations, then we know that we should get two structure functions. So if we average over polarizations, like here, F1 and F2, and well, similar analysis, similar expression we also would have for antisymmetric part, but never mind. Let me just focus at the symmetric part of the amplitude. But here we have actually the loop integral. So we have to extend over all possible momenta and energies here. So then we have to go off mass shell. And then the natural question is what do we have to do? Do we know anything about this amplitude in off shell region? Well, we can try to say something. So one can do the analysis. Let's sort out the possible Dirac structures of this amplitude by expanding in the Dirac basis, and then by doing this we observe almost immediately that we, instead of two structure functions, we actually get seven independent structure functions if we require the current conservation of this virtual nuclear amplitude, which is, by the way, may not be true, but okay, this is standard assumption. So let me also why this may not be true. The current should of course conserve, but it should conserve for the full hadronic tensor, not only for the impulse approximation. And for that reason, so if the current may not be conserved for the impulse approximation, but then can be compensated somehow by interaction effects and then the corrections. But let me stay within this assumption and assume that this amplitude conserves the current, and I will try to figure out how many structure functions we could get here. So we could get 7 instead of 2, and this is because we relax the requirements due to the Dirac equation. So it's quite restrictive requirement that would separate only, if we apply that so on the mass shell, that it will separate only 2 independent structures out of 7. But in the off shell region, so we have to do something with this. And in general, it's somewhat complicated unless we do some modeling and separate some structures, Dirac structures, and work with them. But let me consider some particular example. I think it's useful and working example. Let me assume that the system, that the ground state, the nuclear ground state, is non-relativistic, which means basically two assumptions, that the momenta and energies like that are small compared to the nuclear mass, and so I have to assume that there is no strong scalar and vector fields in the nuclei. Otherwise, I would get in trouble. So the scalar and vector fields would mix the upper and lower components of my operator. So I have to consider explicitly the interaction effects in the impulse approximation. But if I assume that, then I can proceed. So I can write the big psi for component operator in terms of a non-relativistic two-component operator, and so take care of the normalization of this operator. So I have to, by doing this transformation, doing this reduction, I have to take care that the charge actually conserves. So I have the same charge in relativistic and non-relativistic physics. And this gives me the renormalization operator like that, if I require this. By the way, so this equation holds to the order p square over m square, including these terms, if we apply this normalization operator, which is essential point, since the corrections I'm going to talk about are of this order. So then, just doing this exercise, so we arrive from the fully relativistic amplitude. So we arrive to kind of a factorized expression. So we again get the tensor, hadronic tensor, which has only two independent structure functions, which are linear combinations of these form factors I have shown on the previous slide. And this hadronic tensor is proportional. The cross sections and nuclear cross sections and structure functions would depend only on this correlator of nuclear fields, in which you would recognize the usual spectral function. So that would be the expression if I keep the terms of the orders to p square over m square and epsilon. Epsilon is non-relativistic energy over m, including these terms. So here I would like to make a couple of comments. So this if we have a non-relativistic system, then we can proceed to this order and get familiar expressions for cross sections and structure functions in terms of the spectral function. But these expressions hold only to this order. So if I would wonder about the relativistic corrections, then probably something I should calculate some. They may not be expressed in terms of the spectral function. Then in the vicinity of the mass shell, so the hadronic tensor has again the same number of structure functions. That simplifies the life. And so those functions explicitly depend on a new variable p squared. So this introduction serves just to justify this simple formula for. So we get this eventually if you drop some high order, if you stay in the limit of high q square and drop some finite 1 over q square corrections in this expression, then we get expressions like that the nuclear structure function would be given in terms of a convolution of the spectral function p and the nuclear structure function with some additional dependence on off-shell dependence, which we have to do have to think how to calculate. So we are again back to nuclear spectral function. So this is the major quantity which would determine the rate of the corrections. So there are two representations for that. So we can always consider the Fourier transform of the one particle correlator, green function, imaginary part of the green function, or we can insert the full set of states between these two fields operators, and then we obtain a standard expression for the spectral function as a sum over all intermediate states with A-1 nucleon with a corresponding delta function and then the matrix elements. So that what we know from from the whole experience of nuclear physics that at low energies, they actually at low momenta, so the mean field model would give a good description, a good approximation to this quantity. So we have to take care of just the sum over occupied levels in some mean field and calculate the single particle wave functions. But if you want to go to higher energies and higher excitation and higher momenta, then this approximation wouldn't work, as we know. And so one has to do something about the correlation part. And here is a model of the correlated part, which is based just on a simple assumption that the final states are dominated by a correlated pair. There are two nucleons in the final state with a relative momentum p, and some residual system which is might be excited, but the major contribution to the separation energy would come from the relative motion of these two nucleons. So if you just follow this assumption and say that okay, I will model the rest of that sum by two nucleon contribution with some normalization constant, which I don't know, but we'll try to fix from data, and some wave functions, actually two wave functions of that pair. That one which describes the relative motion of two nucleons and center of mass motion of the residual system. Then we would see that that this contribution would be to the structure function would be something like that. The corresponding delta function, which just separates the conservation of energy, averaged over the motion of the residual system, with the prefactor which is determined by the wave function of the relative the wave function of the relative motion here. So if okay, so that's the sketch of these two contributions would look like that. So that the mean field part would give you the strength which is localized at low excitation energies, but this correlated part, which is usually called short-range correlation, has broad peak, and the excitation energy is correlated with the momentum. Okay, so we have to do something about normalizations, and what we know from data that about 20% of the strength is carried is missing in the mean field. So let's just assume that the split of the strength is like that. Then we also have to look at the energies, since these quantities are quantities that would determine the correction to the structure function. So these energies are the separation and kinetic energy. They are correlated by some rule which is called the Colton sum rule, which basically the exact relation if you have only two nucleon interaction in Hamiltonian and non-relativistic system, but could be violated. So if we it's definitely violated. So if we add the three-body force and also relativistic effects in the Hamiltonian. This picture, the cartoon that illustrates how how the binding energy and separation energy and kinetic energy changes with A. So that's a gradually the notations are such that this is a binding energy per one nucleon with a positive sign, and here is a kinetic energy, and this curve is for separation energy. So that gradually rises if you increase number of nucleons.
Where does that come from Chaffee's paper, or?
So actually, this you can calculate from this equation. So
Where
you
does N core come from?
N core comes from Chaffee's paper for a few nuclei.
Okay.
What happens if you try to calculate the corrections? So in impulse approximation, so that the first, if you try the simplest correction, just the Fermi gas, no binding, just the momentum distribution, then we would have something like the curve shown in red here. So this is the pure Fermi gas calculation. Interesting that if we add the binding potential to this, this is just the models of the spectral function. That in Fermi gas with no binding, so we have only the rising ratio. But some minimum we would observe if we try to account for the binding effect. So if we add some simple-minded binding potential of order of say 50 MeV for heavy nuclei, then we would get the green curve here. And the blue one is what we get if we try to plug in somewhat more realistic spectral function, which I tried to describe here. The nucleus here is iron. So so we see the conclusion I would like to draw out of this that something is missing in this calculation, and let's try to improve on that by considering the off-shell effects. So again, so let me make use the fact that the system is loosely bound, non-relativistic, so I just expand in small parameter in the nuclear virtuality, p square or minus m square. So this is nothing else but the Taylor expansion with the first correction which is kept, with the hope that this parameter is small enough on average. So we don't know this function. So one can try to model this in different models, but the approach we would like to take is try to fix it from data by looking at the ratios, at the nuclear ratios, and parameterizing this function and trying to study this ratio and fix this off-shell correction from the data. This is the idea about the value, or the actual value of that parameter. So this is again the nucleon virtuality calculated in terms of the separation and kinetic energies. I have shown on just previous slide. So this is actually a pretty small parameter for deuterium, and which rises up to 0.2 for, in heavy nuclei. So it's kind of averaged virtuality. But before we try to fix it from data, so one has to take care of other corrections. So the impulse approximation, so just to mention, if you calculate the light cone momentum in the impulse approximation, then we observe that this light cone momentum is not one, is not unity. That would mean that there is some missing momentum which has to be shared by some field, and the natural things to do is to consider Pi corrections to structure functions that would compensate missing momentum, missing nuclear momentum. If you look at this smaller x part, then as I mentioned, the time which is involved in the process rises if x decreases. So that the known mechanism for this is so if you think of the particular mechanism, so sitting in the target reference frame, so if you think of a particular mechanism of generating small x events, then this is not the quasi-elastic scattering from bound quarks, but rather a different process which would correspond to different time orderings, to creation of a pair with subsequent interaction with the target. And so if you follow this approach, then and discuss the possible propagation effects of this intermediate state, then the simple thing to do is just to consider the Glauber series of some intermediate states propagating in a nucleus. And so the rate of these effects would be controlled by the effective scattering amplitude for intermediate states. So let me briefly sketch what I'm going to do with the model. So so this is basically Three different contributions to structure functions. So this stands for the proton and neutron contribution averaged with the corresponding spectral functions, with some of-shell corrections, correction which is not known, and we would like to fix it from data, with some pine correction for which we have modeled how to calculate it, and coherent correction which is calculated in terms of effective amplitude, which also we would like to study and then fix from data.
Sergey,
Yes.
let me just interrupt at this point because
Oh yeah.
you have 45 minutes, right? To use that up.
Okay.
That's 26 over 60, and some of those are extra slides, but perhaps what we should do, this may be an appropriate time to just stop this and come back.
Okay. Do you want to stop me right now, so I can stop now, or?
Well, it's either now or 5 minutes from now, because we have Chunzo also scheduled to talk. So I was just thinking that this might be an appropriate time to stop so that you can start up again at 4, talking about the model.
Okay. Again at 4. Okay. Okay. This is logical point to stop. Okay.
How much longer do you think you have? Just so we know that even 4 o'clock, we may have to go at 6 o'clock. Who knows? So.
Well, I will try to be modest. So that if we start at 4 o'clock, so if you give me 25 minutes.
20 minutes,
yeah,
because
okay.
we've got 3 speakers.
Okay.
Okay, very good. So, thank you.